G'day, in this video we're going to be unpacking the dispersion of light as well as the inverse square law. In this video we're covering dot points 3.4, 5 and 6. This will round out inquiry question 4, which looks at properties that can be demonstrated using the ray model of light. The first two dot points in particular focus on each of the key phenomena that we're looking at today, the dispersion of light and the inverse square law and the intensity of light. The final dot point gives us this equation, the last one down the bottom, which is used to quantitatively demonstrate the inverse square law. So our learning intentions for today, first off, we'll unpack the dispersion of visible light when we have white light being refracted. Reviewing some of the qualitative aspects of the inverse square law, which we've looked at in previous videos, and then start to apply the quantitative relationships between the intensity of light and distance from a source. So first off, our dispersion of light. This kind of image is probably something that you've seen quite a lot before. This idea of being able to split white light into its rainbow of colors. Essentially, this is caused by refraction, and the phenomena that we see here is due to the idea that light waves of differing wavelengths will end up slowing by slightly different amounts as they enter a new medium. And so because they slow at different rates, that means that they're going to refract at different angles, which means that they begin to get this splitting pattern, which we see here in the diagram. So under the right conditions, this can result in visibly different degrees of refraction of the components of white light. The bigger the degrees of refraction, the more clearer we see a rainbow style image. And this essentially is how rainbows are created in everyday life. The phenomena is due to the refraction of white light. Something to remember is that blue bends best. It's a little bit of an easy way to remember that blue light or light of higher frequency will incur larger amounts of refraction. Something that we have looked at previously is this relationship between wave intensity and distance. Something that we've unpacked before is the idea that if wave energy was to be emitted outwards, that essentially it would spread further and further out. And because the surface area that same amount of energy covers becomes larger and larger, you have the same amount of energy dispersed over a larger area. This will in turn reduce the intensity of the wave. This brings rise to the inverse square law, which says that the intensity of a wave is inversely proportional to the radius squared, or the distance away from the source squared. This general relationship that's written here can be reimagined or reinterpreted into the formula which is in your data sheet. We're going to have a look at applying that now. So we have I1 R1 squared is equal to I2 R2 squared. So I refers to the intensity of the wave. And for light and sound, we measure this intensity in two different ways. For sound, we measure in watts per square meter. For light, we measure in the candela. The practice question that I've got here should demonstrate this idea that intensity changes depending on how far away we are from the source. So here, the light emitting from an LED globe is 12.7 candela at 54 centimeters away. Calculate the intensity of light at 18 centimeters from the LED. So what I'm going to do first is identify my key data in the data column, then identify the equation and rearrange for our unknown value. So from here, all I need to do is substitute and solve. Here we can see that the intensity of light has increased significantly. The relationship is not linear. In other words, we don't just double the intensity if we halve the distance. Instead, because we've got this idea or concept of R squared, we see that the changes in intensity fluctuate quite significantly compared to the change in distance. And our answer here is 114.3 candela. Really, we should be giving this answer to two significant figures given the data that we were provided. The best answer here would be 110 candela. And with that practice question, we have come to the end of module 3. our final module for the Year 11 component of the course is going to be on electricity and magnetism.